Okay, and then let's talk a couple of terminologies in optimization. First one is function, which is objective function usually, and the gradient and the Hessian. Okay, and we talked about this objective function in the previous slides. Okay, then the next one is gradient. Gradient is simple. So given this objective function, take a derivative with respect to the parameter. That's it. So this gradient is all about the slope of f. Okay. So if we have many parameters, then it's not easy to imagine how it looks. So let's assume that we have only one parameter, w1. Okay. Then when there is a function, then if the current parameter is here, w1 is at this moment, w1 is here, then we can take a derivative, which is the slope. Okay, that is a gradient. And then when we have two parameters, then it's not easy to draw a figure. Then we can take a derivative. It's partial derivative, so we can take a derivative with respect to w1 and w2. Okay, so when we have millions of parameters, then we will take a derivative millions of times. Okay, and the Hessian is the second derivative of this function. Since we have lots of parameters, then as I said, this parameter is a vector, so the gradient is vector. Okay, and then Hessian is all about the second derivative. So the second derivative is a matrix. Look at this one. So we have f, and then we can take a derivative with respect to w1 and w1, and w2 and w1, and wd and w1. And likewise, in the middle of this matrix, we have partial derivative of f with respect to wi and wj. So it's a matrix. Okay, and this Hessian matrix provides information about the local shape of function f at the current parameter w, so which is a curvature information. So which means if the function is really sharp, then the Hessian has a big number, but the curvature, the shape is wide, then the curvature is small, so the Hessian value is small. So based on this Hessian matrix, then we can figure out what kind of shape we have. But again, since the parameters are in the high dimensional space, it's not easy to imagine what kind of shape we have for function f. So if it is a two-dimensional parameters, then we can imagine, we can even draw the shape of the function. But when it is in high dimensional, then it's not easy to imagine the shape of the function. But anyway, mathematically, this Hessian matrix defines and provides that kind of information. Okay. And now we're going to talk about the optimization process, but the optimization process is based on approximation. Okay, so given an objective function, this function is usually really complicated. Think about the neural network. So we have lots of layers. Then this function is quite nonlinear. Okay, then we have a lot of parameters. Then it's really hard to handle this function directly. So as in usual in engineering, when the problem is too complicated, then we take an approximation of the problem. Okay, then if the approximation is reasonable, then the solution is reasonable. But if the approximation is not, it doesn't make any sense, then the solution doesn't make any sense. Okay, so we have a function f of w, then we're gonna get an approximation f hat of w. Okay, and there are mainly there are two approximation approaches. First one is first order based, and second one is a second order approximation. So here we're going to use Taylor series. Okay, so do you remember this Taylor series from calculus? So when we have f of x, then we can approximate this function at a. Okay. So we're going to do the same thing, but in this Taylor series, x is a scalar, but in general, in machine learning, the parameter is a vector. So we just generalize this Taylor series with a vector. Okay, then actually there is a one-to-one correspondence here. Okay, and we don't care the third order part. Okay, so we take first order, or we can take the second order. Okay, so when we take the second order, then the approximation would be more accurate than the first order approach. But there's no free lunch. This second order information comes at cost. So we have to take a derivative, second order derivative. And since W is in a high dimensional space, W is a vector. This gradient is vector, and this is a matrix. Then when the dimension of this W is high, like 1 million, okay, then this one is a scalar, okay, then this gradient is in the 1 million dimensional space, is 1 million dimensional vector. But what about this one? It's 1 million by 1 million matrix. It could be huge. Okay, 1 million would be tiny little parameter space recently. Sometimes we can have 1 billion parameters. Then if it is 1 billion parameters, then most of the time this is not possible. Okay, even with 1 billion parameters, maybe Hessian matrix is not possible without any tricks. Okay, so it's a simple, but it works, and it is better, but it needs some computational cost. So basically, we have two approaches. We're going to talk about a couple of algorithms based on the first one and second one. In the previous slide, we said the Hessian matrix provides the shape of function, but in high-dimensional space, it's not easy to understand or to imagine the shape of the function. So it would be helpful if we understand this in the low-dimensional space, especially in the two-dimensional space with some figures. Okay, so given a functions like this, okay, so in the previous slide, we approximated our function with the second order term. So this one is our approximations. And in the approximated functions, we have a second order term and the first order term. And to understand these equations, we can go back to this term. And I think you are familiar with this term, right? So this equation is second order polynomial equation or quadratic equation. And with this equation, you have a lot of informations. When the a is positive, then this function looks like this. And when a is negative, then the function looks like this. And when a is a 0, then the equation is just a simple linear equation. So bx plus c is something like this or this. Okay, and then c defines the location of these quadratic functions, right? So when c is positive, then function looks like this, and when c is negative, then it looks like this, and so on. So we understand this equation a lot. Okay, good. So from this equation, we can generalize into high dimensional vector. Okay, So when X is a vector, then A is matrix, which is Hessian from the previous slide, and the B is a vector, which is a gradient function. Okay, then to understand this one, we can plot the function in two-dimensional space. Then we can have a couple of different cases. So first, by the way, we can actually apply the eigen decomposition to this matrix A. So then we have eigenvectors and eigenvalue. Okay, then when all the eigenvectors, all the eigenvalues are positive, then we have a convex function. Okay. Then when all the eigenvectors are positive, or some all the eigenvalues are positive and some eigenvalues could be 0, then it is positive semi-definite, then still it is convex. Okay, then when all the eigenvalues are negative, then it is concave, is exactly opposite. And sometimes we can have these kind of cases. Then this one is exactly the same as this one, but in the opposite direction. Okay, and sometimes we have some positive eigenvalues and some negative eigenvalues. In that case, we have a saddle point. Saddle point means in this direction we have a positive curvature, and in this we have negative curvature. So we can apply this equation in some specific directions. Okay, so let's start from this eigen decomposition. When after this eigen decomposition, then we can replace this term with this. Okay, and then X is actually K times V, which means when we have one function in the two-dimensional space, then X means we are interested in specific directions. Okay, and that specific direction is actually eigenvector's direction. Okay, then this Y, in that specific direction, then Y is actually K squared times lambda V transpose V plus something. Okay, so now this is a scalar and this is a scalar too. So finally this is all scalar. And in this case, we can focus on this one, K squared times lambda. Okay, K squared times lambda is a scalar. Okay, so we don't have a matrix here. Instead we have a scalar in that specific direction. Then K squared is positive all the time, and the lambda could be positive or it could be 0 or it could be negative. Then the lambda is positive, which means Y is convex in that specific direction. In this direction, Y is convex. When lambda is 0, then Y is linear in that direction, and it could be concave in that direction. So look at this one. If it is a positive definite, which means all the eigenvalues are positive, then in any direction it is convex. That's good. But if we have a 0 eigenvalue, then in this function, this direction has a 0 eigenvalue, and in this direction it is a linear function. Okay, and when we have a positive eigenvalue and negative eigenvalue, it means in that direction with positive eigenvalue it is convex, but in the negative directions it is concave, so it is a saddle point. You know what the saddle is? A saddle is kind of the seat on top of a horse. So it looks like this. I don't know how to draw this figure nicely. Something like this. Okay, so at this point, this is concave and this is convex. That's why we call it saddle point. Okay, and in this slide, we have necessary conditions and sufficient conditions for local minimizers. So when we have a local minimizer, it has some specific conditions. Okay, so we have a first order necessary condition, second order necessary, and the second order sufficient condition. Necessary condition means if it is a local minimizer, then it should satisfy this condition. If it is a sufficient, then as long as it satisfies this constraint, in this condition, then it is local minimizer. Okay, so I think you're already familiar with this necessary condition and sufficient conditions. The definition of the necessary and the sufficient condition. So let's talk about this first order necessary condition of local minimizer. So W star is a local minimizer and the F is continuously differentiable in an open neighborhood of this minimizer. Then the gradient of this function at this place is 0. That is necessary. If a function has a local minimum here, then at this point, at least the derivative of this function should be 0. Okay, if it is a local minimizer, it should be the gradient of this function should be 0. Okay, and the second order necessary condition says if it is a local minimizer and the second derivative is continuous, then the derivative of function should be 0 and second derivative should be positive semi-definite. Okay, so the derivative of f is 0, and if the second derivative is negative, then it could be like this. And this is not the local minimum. So as long as it is the local minimum, then it should have a 0 gradient, and at the same time, the second derivative should be positive, or it could have a 0 eigenvalue. So in the two-dimensional space, we can have this kind of case. Okay. So these are necessary conditions. So as long as it is a local minimizer, then these conditions should be satisfied. Okay. Then there is a second order sufficient condition, which means as long as it satisfies this constraint, this condition, then it is a local minimizer. It is sufficient condition that the W star is a local minimizer. Okay, so it says if it is a local minimizer and it is continuous in an open neighborhood, then the first derivative is 0 and the second derivative is positive definite. Look at this one. It is a positive semi-definite and it is positive definite. Okay, so it is positive definite, then it is definitely, this one is a local minimum. Okay, then what kind of case we have when gradient is 0 and the second derivative is a positive semi-definite and it is not local minimum. Okay, then when can we have this kind of case? So when the derivative is 0 and the second derivative is positive semi-definite, but it is not local minimizer. So look at this one. So at this point, the first derivative is 0, okay, and second derivative is 0 too, but use your imagination. Okay, so in another direction, it could be something like this. Okay, So in this case, in this direction it is a minimum. It looks like a minimum, but in this direction it is not a minimum. Okay, so we have a positive eigenvalue and the zero eigenvalue, and this is not the local minimum. But if even this direction it is positive, then it should be local minimum. Okay, so this is a necessary condition, and this is sufficient condition for local minimizer.